If it's
Okay.
7:30, you should set your clock back.
Whose clock is that? Mine? No, mine. That the battery's dead in that one.
Well, whoever said it was 7:30, because it's 6:30.
Should
Yeah.
I go ahead? I can introduce myself.
Yeah.
No,
yeah, Carter.
some of you may remember I sent out an email about noticing that some of the guys were off frequency and stuff. Something that I found with could see with the 9700, and also on this my 7300, I noticed that I can tell when people are using too much power or overdriving their amplifier. Well, Rick is about to show us all of the tests that are required to confirm that people are conforming to the specifications of the radio. So with that, over to you, Rick.
Okay, thanks. And yeah, in case anybody doesn't know me, I'm a retired electrical software engineer, and started hamming when I was in high school in 1971, and actually in October crossed 50 years on the air. So I've been a ham for 50 years, and much of my career was working with teams of electrical and mechanical and software engineers designing radio and cell phone test equipment. And that's what I'm going to be talking about. Feel free to interrupt anytime, as if this was an on-the-air net, by saying comment or question, and I'll acknowledge you so you can speak. And let's see, if any of you don't have a copy of the talk slides, let me put something in the chat window. So this chat, let's see if this works. Yeah, it looks like it even converted it to a clickable link. So that's the slides if you don't have them yet and want to follow along or save a copy. And I won't be watching the chat window. In fact, I'm closing that part right now. So do, if you want to speak to the group, just say something like comment or question, and then I'll pause and acknowledge you. Okay, so let me screen share and we'll get started here. Share that. All right, y'all seeing radio test?
Yes.
Okay. All right, well, let's go to this slide. This is the electromagnetic spectrum, and I want to start here because it is the biggest overview I could think of, and also is a quick review of powers of 10 and logarithmic scales and Greek prefixes. So let me just take you on what these axes are here. So this is frequency down at the bottom and shows the entire electromagnetic range. Down here at the bottom, remember, powers of 10 are just a 1 followed by the exponent. So this is a 1 with 6 zeros, or a million, and that's a million cycles per second or a million hertz. And that's about where the AM radio broadcast band is. And wavelengths down here are in the order of a soccer field. So if you want to think of half wave antenna or something like that, they're big, okay? And then as you go up, this would be 10 megahertz, 100 megahertz, a gigahertz. And this is where all of the radio waves are. This is our world. We're going to come back here in a bit. Hams also work some up into the microwaves up here. So this is 10 gigahertz, 100 gigahertz. This is now a terahertz. And, you know, about the only thing we talk about that are tera now is terabyte drives. They're common. But anyway, that gives you an idea of where those are, tera. And then, did you know you have radio antennas in your eyes? So visible light is up here at about 400 to 800 terahertz. And so this is where visible light is. And then you get on up to ultraviolet, soft X-rays, hard X-rays, gamma rays, and more and more and more powers of 10. This is a logarithmic scale. And I just want you to get used to it because some of the things on the test set that I'm going to be showing are logarithmic. And all that means is that a fixed distance corresponds to a power of 10, which is way different than most things like a ruler where every one of these would be an inch. So just a quick review. Let's go to the other side of wavelengths. So I said we started out way down here at the low end with huge wavelengths, and this is a kilometer. That's 10 to the third is kilo, so that's a kilometer. Then 100 meters, 10 meters, 1 meter. 1, 2, 3 more is a millimeter. So when you get up into the microwaves, the wavelength is actually the size of that period, or about a millimeter. You get down into cells, bacteria, viruses, proteins, water molecules, shorter and shorter. And we do have X-rays and some things like this. This is the Berkeley Advanced Light Source. It actually generates controlled soft X-rays, you know, with wavelengths in the order of a protein. But anyway, this is the big picture. And ham radio is actually in 29 frequency bands. The ARRL band plan shows the 18, essentially below a gigahertz, I think, from 136 kilohertz. So let's go down there. If this is a megahertz, right there would be 100 kilohertz. So it's a little bit higher than that. And that ends up being a 1.4 mile wavelength. So if anybody wants to has the field for that, you can do it. All the way up to 250 gigahertz, which is 10 to the 11.4, right about there. So there are ham bands, 29 ham bands here and below, 18 primary down here. And all I did to get these numbers, by the way, is if you take 136,000 and take its log, that's 10 to the 5.1. If you take 250 billion, the log of that is 11.4. So that's it. All I wanted to do on this is get you used to where we are. Now, the next slide is going to show 300 kilohertz, which is about right there, to 3 gigahertz, which is about right here. So this is, again, a log scale. This is 300 kilohertz to 3 megahertz, 3 megahertz to 30 megahertz, 30 megahertz to 300, and 300 to 3000. And each of the colors here is a different radio service. This is what the FCC does, is they make rules for all the radios in this entire diagram. So when you think about it, every radio that is sold in all these different colors and all these different frequencies need to be tested. And so the world of manufacturing radio test is a big one, and lots of customers, lots of providers, and that's what we're going to be talking about. I circled 2 in red. This right here is the 2 meter ham band. That's around 144 megahertz. And then over here is the 70 centimeter band, and that's 440 megahertz. So this is, for those of us that have handhelds and 2 meters and 70 centimeters, this is our little corner of the universe. And here's an example. So this came from the September 2021 issue of QST, and they frequently do reviews on radios like this. And I picked one that is 2 meters and 440 megahertz. And they always have a little chart or table like this. And I highlighted here receiver sensitivity, a very important measurement. We're going to be talking about that and what it means. Whatever it is, they measured this radio at 0.14 microvolts. We're going to be talking about what that is. Here's what their spec is, 0.25. They measured it under various conditions at 0.14, 0.13, 1.0. So this is what we're going to be talking about, is this kind of stuff. Manufacturer's specifications and measured in the ARRL lab. How do they do this stuff? I circled probably the main transmitter one too, which is power. And they are spec'd at 5, 2, or 1. And they measured here 4.7, 2.1, 1.2, whatever. I'm going to be talking about this side of the table and how we make those measurements. Okay, here's an overview. So notice there are 4 quadrants here, and that's intentional for what's coming soon. But notice in the upper left is radio frequency analysis, and the type of instruments that you need there to test a radio are a frequency counter, a power meter, a spectrum analyzer, and sometimes it's helpful to have what's called a storage normalizer, and that means When there's a trace that's about flat on this, you can make it be perfectly flat and do things relative to it. We'll talk more about that. And a demodulator for AM, FM, and single sideband, or whatever it is you're wanting to do. This is the kind of stuff you need for radio frequency analysis. In the area of DC and audio analysis, this is a little more familiar, but again, a frequency counter to count audio, a voltmeter. It's very useful to have DC, AC peak, AC true RMS. Those are the most useful ones. An oscilloscope, a synad or distortion meter, and it usually has built into it things like filters and de-emphasis, a notch filter, things like that. A signaling analyzer. Now, this is something that's rarely talked about in ham radio circles, but it can actually measure DTMF tones and measure what the two tones are, or paging signals, or measure your private line, your transmitter tones. So when you say you need a 123 hertz tone to work in our repeaters, what is your rig actually putting out? How close is it? They need to know that before they can ship the radio. And a DC current meter for measuring battery current when you're transmitting. So again, this is all radio frequency analysis, radio frequency, and DC and audio analysis. In the stimulus side, or generation, for low frequencies, it really helps to have a function generator with sine waves, square waves, triangle waves, sometimes noise, things like that, and a signaling generator. Now, this is something, again, we don't talk about very much, but you want to generate DTMF tones, private line, subaudible tones, paging tones, things like that. We'll be talking some about that. Radio frequency generation is a signal generator. And most nice ones have AM and FM built in. And this one, it's nice too. Notice there's kind of a diagonal line here. If you have a spectrum analyzer and a generator that can track it, this is very useful, having, as your spectrum analyzer sweeps from a low frequency to a high frequency, your generator goes from a low frequency to a high frequency too. This is kind of like how a nano VNA works, or any other swept measurement devices. They've got to have a generator and an analyzer that move along together. And that's spectrum analyzer track gen, or this is a track gen. That's what the storage normalizer is used for. Among instruments that hams want to have, what's missing from this?
I have one question before you get to your question, Rick. I think everybody is probably familiar with most of the terminology there, except synad. Maybe you could elaborate on that.
Yeah, we're going to talk about synad in a bit, so that's coming later.
Okay.
Yeah, but what kind of instruments do hams have that aren't listed here? Claude, you might have said something, but you're on mute.
Well, a multimeter.
Okay, and we've got up here though the DC peak true RMS. A lot of multimeters are average, but actually in radio test you want these three. But yeah, that's good. What I was thinking of here. Well, go ahead.
Meter, maybe? A watt meter, power meter.
Okay, and that's up here.
Yeah.
Yep. I was thinking an SWR meter, and I've been mentioning the storage normalizer, and keep in mind this whole subject tonight is testing radios. So it's whole radios and just radios. We're not designing a radio. There's a lot of other test equipment you might want to design one. We're also not generally testing antennas, although the test set that I'm about to show does a little of that too. Anyway, that's all I wanted to say, is just remember this is for complete radio test. You want a radio, before you ship it, this is how you're going to test it. This is the test set that I'm going to be talking about. This is a Hewlett-Packard 8920A RF test set, and it was developed from 1984 to 1991. I worked on this from beginning to end, and by the time we were fully staffed, it was with a team of 2 mechanical engineers, 10 electrical engineers, and 8 firmware software engineers. And for the last few years, that's kind of what this kind of thing takes to develop. And it sold back in that day for $20,000 fully optioned. It is an RF and audio generator, RF audio analyzers from 0.4 to 1000 megahertz. So again, on that big spectrum chart, it's from below the AM broadcast band up to above the 900 megahertz band. It's made for AM, FM, and single sideband radios. I did this kind of fun, inflating that price using standard inflation would be $50,000 in today's dollars. It's now obsolete, discontinued, and you can get them for about $2,000 used on eBays. I've seen them as high as 3,000 and down as low as 800. So I just looked at completed auctions recently, and so anyway, I'm not sure why the big disparity, but probably has to do with their calibration history, would be my guess. And here's a key statement. I'm going to read this twice, but an RF test set is just a very good general purpose transceiver with various detectors throughout its block diagram. Notice there's even a microphone accessory jack here. As an option, you can get a push to talk microphone that turns this into a 50 milliwatt transmitter receiver. And let me go over the connectors too. So it's pretty simple here on the front panel. This is RF in out. So if you've got a transceiver, this connects to the antenna and it both takes RF in and puts RF out. It's got a 60 watt attenuator right behind it. So you can put quite a bit of power straight into the front panel. They say 100 watts intermittent. I think it'll take that for 20 seconds. But that's a big deal, having a connector that'll take 100 watts right on the box. Because of that 60 watt attenuator, the levels that both are measurable here, and it'll only measure high powers and it'll only put out low signal levels. It's meant for a direct connection to the radio. This is for high powers into an antenna, with still high powers being 50 milliwatts, but it'll easily transmit around a room. And this is an antenna input, which is a high sensitivity antenna. And they accept this, if you see it, we ship with it too, but this is just a telescoping antenna. And it's just meant to get the signal from the front panel into the immediate room or pick up stuff around the room. Or when you're on a mountaintop, you can actually put it on and pick things up off the air. The microphone accessory jack, as I said, is for a microphone. It also has a push to talk relay in it so that the box itself can tell the radio when to transmit. When it's receiving a signal that's being transmitted, it has a volume and a squelch control and a speaker on the underside of the case so you can hear it. And then it's got audio out and audio in. So this just is a signal to go out to the microphone of the radio. And this comes back from the speaker and can be, the reason there's two connectors here is it can be floating. So you can either have this reference to ground or totally floating on your audio input. Let's see, again, all this is, think of it as a very good general purpose transceiver with detectors throughout its block diagram. Now that's about all I'm gonna, let's see, let me check and make sure what else I had to say about this. One thing that I'll comment on, back in the 80s, this was quite the unique thing, but this was when HP introduced the detented push knob. So that knob right there, you can push it and release it and turn it, and it's got 64 detents. So it actually has a soft click as it goes around. That one device can pick any field on the screen. The cursor kind of goes through the columns like this. And then if you push it, you can put any setting on the knob. So for example, where's our power? It's off at the moment, but you can adjust your output power in terms of microvolts or dB. And so you can adjust it logarithmically, 1 dB per step or 1/10 of a dB per step, or in terms of volts. So anyway, this is very general purpose. You pretty much run this whole instrument by keeping your hand on the knob and occasionally going to the buttons to do things. So anyway, but that's all I'm going to talk about the user interface. Next, I'm going to just show what it can do. Okay, so let's look under the hood. Oh, there. This is the block diagram, and I just want to bring your attention to the same 4 quadrants. So this is RF and spectrum analysis. This is audio frequency analysis. That's what AF stands for. This is audio frequency generators, and it has two in it, one that's capable of just sine waves and DC, and another one that is infinitely complex. It's got about 16 screens of information to run this thing, but it'll do subaudible tones, DTMF, paging, various cell phone signaling. So anything that travels in the audio channel, this will do. But anyway, audio generation and then RF generation. So you need not understand a lot of this symbology. They're all standard signals. But just notice here in the RF spectrum analysis, these are the front panel connectors, the antenna input for making sensitive measurements, the duplex output for sending large signals out, and then the RF in out with the big attenuator. So this is going to take high power in, low power out. The red marks are what measurements you can make. This is TX power, spectrum analysis, transmitter frequency, or error from the tuned frequency, kind of the same thing. This also will demodulate AM, FM, or single sideband. The audio analyzer can analyze either AM, FM, or single sideband, or the speaker input from the radio. So this is where the speaker comes in, goes in here, and you can do all this analysis on it. This is where we have an oscilloscope, a signaling analyzer. So everything that this will generate, this will analyze. A synad meter, more about that later, distortion, audio level in either volts or watts across an external resistor, like a speaker. So if you have an 8 ohm resistor, for example, out here on the audio input, this will read watts across 8 ohms. Audio frequency, DC level, and DC current here. So all of these measurements can be changed with filtering, de-emphasis, a notch, a speaker with squelch, and you can pick what you have up here. So this is kind of a general purpose analyzer. Down here on the sources, the two sources or a external microphone or rear panel modulation input can have their levels set and then be routed to either an AM summing node, a FM summing node, or out the front panel. So you actually can combine multiple signals and have them either go to FM, the frequency, AM, the amplitude, and then that comes out the output either directly into the antenna of the radio or out the duplex output. Okay, so this is a summary. A test set generates and analyzes radio and audio frequencies connecting key signals in useful ways. That's all I'm going to talk about here, with very good specifications. And that's key. Anything this product does, as far as the radio is concerned, better be perfect. In other words, we've got to be way better than the radio specs so that any degradation that's measured has to come from the radio, not us, is the idea there. Okay, let me just revamp here. So when you're testing a transmitter, what are you doing? You generate usually a 1 kilohertz sine wave out your output port, out here to the audio out that goes to the microphone of the radio. So it's just like whistling into the microphone. That's essentially what you're doing, but in a very controlled way, exact frequency, exact level. The transmitter transmits that, and we have usually a direct wire connection here. This is now taken as an RF input. You can measure transmitter power. You can demodulate AM, FM, or single sideband. Oh, I should have said this first. While you're still in the RF world, you can do spectrum analysis or count its frequency. Then after demodulation, we can do things like measure distortion, measure transmitter current, measure signaling analysis. That can be the quality of the, well, distortion is the quality of the sine wave that's coming back. Signaling would be where you can measure things like subaudible tones, DTMF tones, things like that. That's about it. So the red boxes, it's actually pretty simple. Now there's a lot of generality we're not talking about, but generally speaking, when you're testing a transmitter, you take a 1 kilohertz sine wave out into its microphone, take its transmitter signal back, measure stuff on that, demodulate the 1 kilohertz tone, and do all sorts of measurements on it. That's it. break in with any questions if you've got them on this. That's all I'm going to say about testing a transmitter. Testing a receiver now, you start with a pretty complicated signal generation scheme. So again, most common, you take a 1 kilohertz sine wave, FM modulate the signal generator. So now we've got a very accurate FM modulation on a signal, run it out the RF output port. So now this is going into the antenna of the radio. So very precise 1 kilohertz, very accurate deviation, very accurate RF frequency, and probably most important, a very accurate RF level. Down at a very, very low level typically. This is very important. We'll get to that when we get to some of the actual tests. So that's it for receiver test. Again, it's an audio source, FM, or modulating the signal generator, however you want it, going into the radio's antenna. Then the radio, which you'd normally be listening to, we tap its speaker into our audio input, usually across an 8 ohm or 16 ohm resistor, and then measure everything to do with that. So we can measure synad, level. This might be, you know, a half a watt into the 8 ohm resistor. A lot of tests need that kind of power level to make it. And we'll talk more about synad. But anyway, that's it again. It's just complicated generation, sine wave to FM signal coming out. Goes into the radio, it demodulates it, and we tell how good of a job it did by what comes out of the speaker. Okay. All right, these are all screen captures from here on out. I don't do anything more with the block diagram or the front panel or any of that. I just want to show you what it'll do. Main order of this entire talk is 3 radio connection scenarios. That's over the air, which is 0 cables. And there's a lot you can do to test a radio by just having it in the same room with a test set. The antenna only, which is 1 cable. There's more you can do there. And then lastly, the way they would do it on a manufacturing floor is 3 cables, which is the antenna, the microphone, and the speaker. So each scenario can test a little more than the previous one. But this screen shows a Bofang UV5R over-the-air TX test. The radio call button generates a 1 kilohertz tone. And I don't know if you knew that, but turn on my Bofang, and it's working into a dummy load. But if you hold down the push to talk and push the call key, it actually transmits a 1 kilohertz test tone. And this is that's one of the reasons I tested this radio is not a lot of handhelds do that I have. And but anyway, it's a very nice feature if you want to test the radio. So just the radio itself can put out a 1 kilohertz tone. And that allows us with the test set, just having an antenna, that's all I'm using here, to measure. So let's look at some of the settings first. I have the test set manually tuned to 146.5 megahertz. That's right near the 146.52. I'm measuring the antenna port from the test set. I'm doing FM demodulation. I'm doing audio filtering from 50 to 15 kilohertz, which is pretty much wide open. I am using de-emphasis, which most FM receivers use, and that's about it. And we can measure a 90 hertz transmit frequency error, which is not bad. Anything under 100 hertz, I consider pretty good. But notice we're doing this without even being connected to the radio. The FM deviation is 1.9 kilohertz. And although it's not spec, my guess is they set it to 2. 2 kilohertz or 3 kilohertz is generally around where you want your voice to be. So that's a 2 kilohertz deviation. And then we can also count the frequency. So this is a really good 1 kilohertz tone, okay? I was surprised at these results, honestly. It's kind of like, wow, 1.94 instead of 2, 90 instead of 0. And remember, this is 90 hertz out of 146 million hertz. So that's pretty good. And so anyway, that's a simple transmitter test, just using an antenna. Next, all I did here, same situation, but I switched this measurement from audio frequency to distortion. And this shows that the kilohertz sine wave is distorted 4.5%. And for a communications transmitter, that's okay. It's not stupendous. For an audio file, that would be terrible if you're trying if you're trying to measure your very expensive stereo set or something. That would be totally unacceptable. But this is a far cry from that. You know, if you can get FM radio quality or whatever, that's great. So 4.5% is good. And all that's doing, by the way, is measuring the amount of energy in the kilohertz sine wave relative to all of the noise. And what this is saying is all of the noise is 4.5% of the signal. So that's kind of a total energy. And that's way down there. In other words, think about that. 4.5% of the energy in the noise is like, that's, you might say that's full quieting. You know, you might not even hear that. Next, the test set allows you, and this is just for quality purposes, I often do this just to make sure it looks like a good sine wave, and this did. Sometimes you can get kind of scary results, like this might have some ripple in it or something, that some high frequency ripple, and it might be that, okay, the total contribution is small, but it shouldn't be there. It shouldn't be the sine wave and a bunch of little ripples. It should just be something like this. And now I want you to look at the scope here and notice some things. So this horizontally, it's like a normal oscilloscope. The time per division is 200 microseconds. So from here to there is 5 divisions. That's 1 millisecond or 1 cycle of a kilohertz. So that kind of is good check. But notice this scope has something very odd. Vertical per division is calibrated in kilohertz. And that's because it knows we are looking at an FM demod signal over here in the corner. So it is going to calibrate the vertical scale in terms of kilohertz of deviation. And so what this is showing, it's 1 kilohertz. So this is showing a 2 kilohertz up, 2 kilohertz down, or 2 kilohertz peak, which is what we saw on the other screen. So this scope actually also has markers that you can set. That's other settings that are off on, you can select whole settings of controls over here. But with the markers, you can put for example, a marker there and a marker there, and it would read 4 kilohertz peak to peak and half a millisecond. And those readings are over here. So I'm not really using that right now. These are just showing wherever the dot is. I'm not sure. Oh, that's center screen. The marker happens to be right there. But anyway, that's the oscilloscope. So the neat thing here is it's calibrated in kilohertz because we're looking at FM. Any questions about that? Okay. Next, let's go back and remember this is just off the air, but I saw something unexpected here. So this shows, first of all, let's talk about the axes. This is a center frequency of 500 megahertz. So that's right here. And then a span of a gigahertz. So that's 0, 500, a gigahertz. So from left to right, this is the full range of the product from 0 to a gigahertz. And a little oddity goes on down here at 0. You'll see that's called LO feed through, but when you're scanning all the way down to 0, it'll do it, but there's actually a little anomaly down there that you ignore. And here at 146.5 megahertz is the signal we expect. And what is this? Okay, that's not down very far at all. That's maybe 18 dB. Yeah, in fact, I used the marker functions to measure it. This is 72 megahertz higher and 18 dB down. And I just wanted to bring up, this is the kind of thing you can see because that should get your attention and go, what the heck is that? And then you remember, oh, I'm checking this with only an antenna. Anything that's coming in on the antenna is being shown here. So this might be my PC, some appliance in the house, who knows what it is. No conclusions yet, but that would be something that if I was testing this, I would think, I want to look into that further. And I didn't at this point because I'm only doing an over-the-air test. But that's the kind of thing you can see. So you can actually measure 72 megahertz. It's not harmonically related. That would be 146 megahertz up. And it's not down very far at all. And I didn't look into what that was, but it's just, I would ignore it because right now I'm on an antenna. Let's see. Okay, the next slide. This is the same thing, testing over the air, but now I turned on the repeater function. So, you know, the Baofeng will generate 123 hertz tone. And I thought, let me try and see what that is. So I took the Baofeng and turned on the generate 123 hertz tone. And now the test set needs some special settings for this. So notice I'm still doing FMD mod, but I'm limiting the audio pass band to 20 hertz to 300 hertz. So I've kind of filtered just that range. So this is all the subaudible tones and things are coming through. And that's what I want to measure. And the TX frequency error up here, it was 90, I think before, or something like that. But anyway, and now it's 83. There's a little noise on it. But notice what we have here, 122.95 hertz and 595 hertz deviation. Again, this was surprisingly good. This means, you know, that's what, 0.05 hertz off of 123 hertz. And usually private line tones are set for 600 hertz. So this is fine. And that's generally not spec'd. It's just kind of a nominal. That's where you want your private line tone to be. So this is well set. So again, so far I was pretty impressed with this Baofeng. So anyway, that's something else. We haven't even connected the radio yet, and you can test that. Here's one last thing that just a test set would do, but once it's configured, you can measure DTMF tones. Now, all I did, let me turn this on again. When you have a DTMF pad, if you've ever looked at what's actually going on, every tone is generating 2 tones. That's the dual tone multiple frequency. And if you've ever seen a chart of the numbers on the keypad versus the frequencies, a diagonal is 159D, and that sounds like this. So all I did there was go down the diagonal of the DTMF pad, and the test set will measure that. So what this says is I heard a 159D. Here's all of the low tones. Here's all of the high tones. So we have just checked the entire DTMF encoder to see what frequencies it puts out. And we could check this against the standard. I don't recall what it is. I think it is 697 and 1210. I'm not sure, but anyway, we could look that up. But anyway, it's also measuring the amount of time that it was on and off. I did it for about like I did it there of just do, 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 do. And that is a half a second on, a half a second off, half on, half off, half on, half off, half on, and then off. So a lot of useful information here. And these on and off times are useful because many handhelds have an auto dialer memory where you can put in whole phone numbers or whole sequences and it goes beep, boop, 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 like that. The on and off times are frequently very important. And sometimes for certain radios, they have to be set so that the receiver, you know, is expecting 50 milliseconds or 100 milliseconds or 200 milliseconds per beep. Telephone systems are very flexible. You know, you can do it long, short, whatever, but radios sometimes, if you're receiving a DTMF tone, have to have these times very specific. Let's see what else I had to say on this. Yep, I'll just go into it, but the test set, it not only checks things like this, but it does different radios for marine, fire, military, and all do different kinds of in-band signaling. So these are things that you'll hear with your ear, but they mean something very special to the receiver. That's tone sequential. POC-SAG is a pager. EIA, CCITT, these are various test standards. GOLE is a pager. AMPS, EAMPS, and NAMPS were cell phone standards, as was TAX, ETAX. These are back in the early 90s standards. NMT 450 megahertz band, NMT 900 megahertz band, et cetera, et cetera, et cetera. So this kind of slopped over into cell phone test back when cell phones were analog, like the early 90s. Okay, now we're going to go to receiver test. And I move quicker from here on out. But receiver test with just an antenna, there's not a lot you can test. So all I'm doing right now is the test set is transmitting out an antenna and the receiver is receiving. But I can hear a tone in the radio. The receiver works. So this is a lot of functional test right here. I'm generating 146.5 megahertz RF signal at as big an amplitude as the test set will put out. And this is actually uncalibrated, but it's still reasonably good. It's out of spec, but this is 63 milliwatts is 18 dBm. It's going out the duplex port. So this is where we can get the most power out. And I've just got one of these antennas on that port. And what else? We can see I'm generating a 1 kilohertz audio tone, and it's being used for FM modulation at a 3 kilohertz deviation. I'm also, talk about this on the next slide, generating a 123 hertz tone with a 600 hertz deviation. So I'm all ready to go into one of our repeaters if I were to change the frequency, but I'm going to show that you can actually test that on the receiver too. So just the fact that you can hear a kilohertz tone coming out of the receiver says this radio is probably at least functional. And so that's what you do here. Just say, yep, it works. Okay, and by the way, I want to emphasize this. For all the slides to this point, we haven't yet even connected the radio to the test set for everything we've been doing, but now we do that. So this is a Bofang 1 cable TX test. So I have it set to high power, and I'm using the call key to transmit a 1 kilohertz tone again. So we're getting, these three are the same results we got before, 89 or 90 hertz frequency error, about 2 kilohertz deviation, a good 1000 hertz tone. But this is new and very important. So the spec is 5 watts, but they don't give any kind of an accuracy to that or anything else. And 4.86 is close enough. You know, it's kind of, it should be about 5 watts. And I went ahead and did the calculations. That's actually 0.12 dB low. That's not very low. You know, that's pretty much, you know, another measurement like a ham power measurement might well call that 5 watts. There's easily 1/10 of a dB error in those. So anyway, that's it. Now we can measure power. Now I didn't hook it up, but we also could measure battery drain if we had that connection. You know, if we were driving this with an external battery, you can run the current in and out of the rear panel of the test set and measure how much current it's drawing. Okay, that's all I have on that slide. Next, now that we have a good 1 cable connection, the spectrum analyzer should be showing only what's coming from the radio. So now we should take notice. Take notice, first of all, that signal, it might be this one, I'm not sure, but it's way further down than it was in the previous slide. So I feel good about that. Signal was probably coming from something else. But some things to notice. Here's, let me talk about the spectrum analyzer again. Remember, this is 0 to a gigahertz. I think I forgot to talk about this. And this is a log scale, 10 dB per division. So from there to there is 10 times less power. Another step is 10 times less power. Another step, 10 times less power. Another step, 10 times less power. So this is down about 10, 20, 30, 40, a little more than 40 dB, okay? So that's 1/10,000th of the power, 1/10,000th of the power. So let's call it 40 dB down. What is it? You might notice this is 146 megahertz. This is right on the harmonic, which is 293. So twice 146.2 is 293. You can go 100, 200, very close to 300. Okay, so that's the second harmonic of the carrier. And then notice equally spaced out here is another one. That's the third harmonic. And if you just take 146 times 3, that's 440 megahertz, which, by the way, is yeah, you can, that's one of the reasons the ham bands are sometimes harmonically related, is so if you're putting out junk, it falls in another ham band. Okay. So the third harmonic here is right at 440 megahertz. It turns out exactly there. I didn't even notice that when I picked 146.5, but let me check that. I think it is exact. 146.5, 3 times is, yeah, 439.5. Okay. But if easily, you could move this up a little bit. This would be in the 440 band. Anyway, how good is this? So these are like second and third harmonics, 40 dB down. I went to the UV5R specs and it says, and I quote, spurious emissions less than -60 dB down here. This is way out of spec. And when they say less than -60, that is a pretty good radio spec. And I wouldn't expect a Bofang to do that. And it fails according to their specs miserably. Yeah, this should not be that high. And I honestly did not look any further into these two things, but they are clearly not 60 dB down either. That would be down here. They're a good maybe 12 dB above that. So this thing is putting out that, and the harmonics. I mean, this, and the harmonics. And we could, I bet, figure out what these things are there. But in any case, that spec, no, didn't make it. Okay, now with one cable, we can, there's still not much we can do, but receiver sensitivity can be estimated with one. Now, this is where I'm going to talk about SYNAD. SYNAD is a very complicated subject, what it is mathematically and all that. Oops. Didn't mean to do that. All SYNAD 12 dB means, so let me say this. Receiver sensitivity is typically what level comes into the antenna to give 12 dB SYNAD out of the speaker. And 12 dB SYNAD is just a formal thing that you can measure, and we can't hear because we're not connected to the radio speaker yet. But when you've done these tests day after day after day after day, you get to be used to what it sounds like. And I would say subjectively, so this is definitely not an accurate measurement and everything, but notice what I did. I had to drop the level to 0.112 microvolts to hear what you're about to hear. And this is actually a recording of a true 12 dB SYNAD. So all that receiver sensitivity mean, and let me say this, I would describe this subjectively as, if you heard this on the air, I'm going to play it in a second, but you'd say, hey, there's strong static on your signal, but I can still copy you okay. All right. And tell me if that isn't about what you're about to hear. This is a recording of 12 dB SYNAD, and I'll leave it on for 10 seconds. Okay, so I wanted to get the idea. You're definitely not going to say full quieting or partial quieting. You're going to say there's quite a bit of static there. And but you can still definitely pick out the kilohertz tone. Okay. So all I want to say about SYNAD is what's important is it's a technical way of saying it sounds like that. Okay. So receiver sensitivity is just where you drop the level into your antenna down into very low levels. And keep in mind, that is 1/10 of 1/1,000,000th of a volt. That's what's going in the antenna, and that's what your radio can receive. And 0.1 microvolts is typical. You might remember that Alinco that we saw measured at 0.14. This one's 0.11. Now I did this just by the sound, and you'll see later on I test it accurately, and this is off by quite a bit. It's the real answer is about 2 microvolts. But anyway, I'm considerably low here when I tried to adjust for that sound.
Rick,
Yes.
would this be what we used to call a signal to noise ratio?
Yep. SYNAD and signal to noise ratio and distortion are all very, very closely related. And I'm not
Okay.
going into the math behind them or anything,
Yeah,
but they all just relate the signal energy to the noise energy. So signal to noise ratio, SYNAD, SYNAD stands for signal, noise, and distortion. Signal
Okay.
input to noise and distortion. But anyway, yeah, they all just relate the signal to, well, I say it this way, they relate what you want to what you don't want. That's it. So distortion, noise, that's all stuff you don't want. And the signal, the pure 1 kilohertz is what you do want. And by the way, that's what you need the notch filter for in the audio analyzer. It will notch out the 1 kilohertz tone and leave everything else. So that's what you want for SYNAD. You want to leave noise and distortion, but take out the signal and then measure just the signal. That's it.
Okay,
Okay.
thanks.
Anyway, so that was that. Okay. Okay, the rest of the talk, and it's just a few slides, is on a 3-cable connection to a Kenwood TR2500HT. And notice now, this is what they're going to do on a manufacturing floor. And I've connected the antenna and the speaker and the microphone. So you typically need some custom cables to be able to do this to the BNC connector on the connectors on the test set. Shouldn't say BNC, but here is a BNC cable through an adapter going to RF in out. So now we can both generate and measure accurate signals. This is just like the 1-wire connection. But now we've hooked up our audio output to the microphone of the radio and the speaker output back from here to an 8 ohm resistor. You can't see it across this, but there's an 8 ohm resistor between those two things, and into the audio input. And so now, and then this last connection is, I mentioned this was an accessory connector, but this wire, there's actually some parts in those connectors, but this allows the test set to tell the radio to transmit. So now total hands off of the radio, and this is important, I will get to it later, but this can not only tell the radio to go, it can tell the radio to transmit, measure everything you want to do on transmit, tell it to go to receive, measure everything to go on receive. And if the radio had some external way to change its frequency or change other settings, this box can do that. We'll get into that in a bit. But right now, all we're going to do is do microphone, audio out to microphone, speaker in to audio in, and we can also make it transmit or receive here. And this is how they do things on a manufacturing floor. A little bit of nostalgia. I have to put this in here. This is me in 1990, before the 8920A was introduced, demonstrating it to Bill Hewlett. He is the Hewlett in Hewlett-Packard. And he was 76 years old at the time and was still active in the company and toured divisions to keep an eye on them and see what products they were working on. So this is about a year before we introduced it. He passed away 11 years later in 2001. And what's that in my left hand? That is my Kenwood TR2500. And I had it during the development of this product at work most of the time and was testing it all the time. And so that's what I'm using here. And all else I wanted to say about this slide is notice my hair was longer and a different color back then. Okay. Next, with a 3-wire connection, we can really make things happen here. So we'll start with the transmitter. Settings show a 5.3 millivolt, 1 kilohertz tone into the radio's microphone. This level was picked because that's what generates 3 kilohertz of deviation from the transmitter. And this is a test called microphone sensitivity. So most ham radios don't spec this, but some radios do, is when they use external microphones, particularly, what voltage is necessary to give 3 kilohertz of deviation. So I dialed this in intentionally, watching this to get 3 kilohertz. So there's our accurate 1 kilohertz into the microphone. And then we are manually tuned to 146.5 megahertz. Looking at the RF input, what else is normal here? 300 hertz to 3 kilohertz. So this is where we want to make measurements just in the audio pass band. So this is where voice measurements are usually made. And that's it. So we can measure here the transmitter frequency error, and it is -2.5 kilohertz off. And that's terrible. but I wanted to capture it because I thought, oh my gosh, I haven't tested this radio in probably decades. And this really surprised me. It's way off. I have it set to low power, and the specs on this radio, remember this is an early 1980s radio, say 0.3 watts approximately, and I got 0.2 watts, a little bit less than that. So 0.167, it's okay. It's putting out around 0.3. What else? The distortion, 7.3%. That's getting pretty bad. I mean, something's wrong here. And so the next slide shows 2 days later, I couldn't go on with this radio being this bad. I downloaded the rig service manual, which I had never downloaded before, and it's still out on the internet. Took apart the HT and adjusted an inductor following the service manual to improve the TX frequency error. So now it went from minus 2476 to plus 44. I thought that's great. Power's about the same, 0.16, 0.17, 3 dB. And notice what the distortion did, by the way. And this is explainable. When you have a carrier frequency off that far, it's not centered in the intermediate frequency filter. It is getting one side distorted. So like as the frequency goes one direction, it does it well. As it goes the other direction, it hits a filter skirt, and it's just terrible for distortion and all. So this dropped from 7.6 to 2.6, which is nice. That's even better than the Bofang that we measured earlier. So anyway, this is what you can do with a test set. Real life example is I actually adjusted the frequency while it was doing this real time and then put it all back together and measured it. Okay, and here is an accurate receiver sensitivity test. So notice that I have dialed in an output level of 0.216 microvolts. And I've got SYNET is a very noisy measurement. So I've got averaging turned on. That actually takes a number of settings and runs an average so you can see it settle in. So 12.4, that's close. And so all this is doing is measuring what you heard. In other words, if we were to turn, I don't have this hooked up now, but if you were to turn the speaker on the test set, you should hear just what you heard. But this is proof. This is the numbers that you want to dial it into. So I think I had 0.11 and it's 0.21. So I was almost off by a factor of 2 or 6 dB because this is voltage. So anyway, my by the ear measurement was not nearly as good as it would have been 30 years ago, but that you get the idea. You can at least tell the radio's marginally good. You know, I got 0.1, this is 0.2, it's still good. By the way, the spec is, I had to look that up. Where was it? Yeah, the spec is 0.2 microvolts on this Bofang, or the Kenwood TR2500. I looked it up there. So it didn't make spec, but again, it's 30 years old and just barely missed. So instead of 0.2, it's 0.216. So I'm happy. Okay, let's see. Slide 27. We're getting near the end of the talk, and I want to show some other things you probably haven't seen before. So this is just some fun stuff the test set can do. This shows my Yaesu FT70DR. So that's a Yaesu System Fusion transmitting Yaesu System Fusion C4 FM. And you have to wrap your mind around a whole new world here, but the test set is demodulating the FM and showing it on its oscilloscope. So let's look at these settings. This is 500 microseconds per division. So a millisecond is 2 of these. There's a millisecond. And again, we're calibrated in terms of kilohertz. So this is a peak of +2 and a peak of -2, roughly, you know, maybe 1.5. But notice some interesting things. It turns out, knowing what C4 FM is, it is a 4800 baud, 2 bits per baud, or 9600 bits per second digital transmission. So there's a lot of technical stuff in here, but let me just say again what you're looking at. So C4 FM means the continuous 4-level FM modulation. So whenever you hit the transmit key, this is what's coming out. That's the continuous. 4 level says it's either around there or around here or around there or around there. Because of the transitions, this is an impure science, but a receiver will actually detect, okay, that must be up 2. That right there must be up 1. It's definitely above the axis, and it's doing filtering and other things to guess which one of these it is. But analog, it goes like this. But every 1/4800th of a second, that's 208 microseconds, or 0.42 divisions, there to there to there to there to there. This is transmitting 2 bits. 2 bits can be either 00, 01, 10, or 11. So that's what this is doing. This is saying like 00, 01, 10, 11. So you're getting 2 bits, 4,800 times a second, or 9,600 baud. And remember, this is now the kilohertz deviation is normal, about plus or minus 2. And the rate is higher than you would normally. We think of speech being 300 to 3 kilohertz. This is 4,800. So it's up there. It's higher than a normal voice radio is going to do. And the bandwidth required for this is a little higher than a normal voice bandwidth, but not exceptionally. Instead of 3 kilohertz, it's 4.8, so it's up there, but you can imagine that a radio that works for audio could easily be designed to handle this as well. And then all the rest is just the decoding, mapping this to bits 4,800 times a second. And you know exactly when to sample it. That's another thing because it's continuous. And you can make judgment calls of where it's been and where it's going. And there's even encoding in the bits. Like a lot of times these things, you don't have to get every bit sequence right. Like if you're wrong, the code that's coming is what's called an error correcting code. So you can both detect an error and correct it. There's redundancy in what they're sending. And so this is it. Your voice actually goes into what's called a codec. It converts your voice into digital. And that's not just sampling. It's much more complicated than that. It has to do with, there might be a special short disk bit sequence for t, ch, s, b, t, those type things. It's actually encoding human speech. And the most common sounds you make are just a few bits. And that's how it puts so much information into a bit stream. And you still have extra bits for error correction and detection and stuff like that. But this is it. So this is what C4FM looks like. Any questions on this? Okay.
Yeah, it kind of surprises me that the signal looks like that when the C4FM modulation is so crisp and clear.
Yes, and what's going on is, remember, this is the over-the-air modulation. What comes out of it is all the decoded bits. Like imagine what's coming out of this is 9,600 bits a second. And that has encoded 1 second of speech. So if you say like 73, that was s, e, v, n, t, f, e. That's it. That's what's being encoded here. Plus the slur, the intonation of your voice, things like this. But that's the way a codec works. And by the way, codecs are highly proprietary and frequently patented. And that what they're trying to do is just say, I can get your speech into fewer bits than the other guy. And people will pay a fortune for that because all that can go across the air is 9,600 bits a second. And the more they can put in error correction, background noise reduction, that's going on here too. It's actually sensing what's your voice and what's noise and getting rid of the noise. It's all done in bits and digital. But all that's going across the air is 9,600 baud. All that good noise, noise reduction, matching your voice, all of that is in the codec. So that's voice to bits and bits to voice. And that's it. But this is what goes out over the air. Any other comments or questions?
Yeah, I was saying, looking at that, I would imagine I'd be hearing a lot of noise in that transmission. That's pretty
Yes,
impressive.
in fact, what this sounds like, if you listen to Yaesu System Fusion, 4,800 hertz is way up there. Like, right now I'm talking 300 to 3 kilohertz. You're getting almost all of it. 4,800 hertz sounds like shh. That's way up there. And that is 4,800 hertz. That's what you're hearing. You're hearing the different bit transitions and they're coming at 4,800 a second. And that sounds like shh, just up above the audio band. So anyway, yeah,
So
that's
that
it.
Rick, that that image that you caught there, I assume that was just a frozen image from a split second.
Yes,
And
this says instruments held. I actually did this about, gosh, 7 or 8 times until I got one. I wanted a neat little pattern like that in it where it was going up and down and up and down so you can see and then I also wanted to get the peaks and the valleys. But yeah, this took several times to hit. And then I thought, there's a good one. And I went, hold it, and hit the hold key.
right. So I could imagine though what you really saw on the screen was just a blur there, kind of centered on that middle axis.
Yeah, what happens if you just have the scope, it always triggers here on the left side with a rising edge. So there was always something like that, but everything to the right, every scope trace would go boom, 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 like that, however I said it.
Yeah.
So yeah, and
As fast as your scope could trigger.
yeah, and this scope, by the way, does have all the normal scope things, auto, normal, single. So you can set it up for single shot and trigger it and then say, did that one look good? Nope, try another one, try another one, try another one, so you can eventually get something that looks like this. Any other comments or questions?
So now I'm understanding this. This is what it would sound like if you were on an analog UHF radio without the C4FM turned on.
Right, exactly. This, you're looking right now at the analog FM signal, which is encoded bits. By the way, D-Star, DMR, Yaesu System Fusion, they're all this. All the smarts and everything are in the bits, but still what goes out over the air is analog FM. That's pretty much all you can do to the signal, but the way it varies, what frequencies it goes to. By the way, this is also, I'll broaden it, FL Digi, a lot of its modes and everything, all they're doing is FM, but the way they put the bits on and take the bits off is unique to a given mode. And some of them, like QPSK 31, they have an extreme amount of error correction and stuff in the bits. So you can transfer bits like this. That's a bad example because it uses mostly single sideband, but still it's just AM or single sideband analog. You can hear it. That's it. But what you're hearing is the encoded bits. And then all of the smarts of the system are what they put into the bits, sound to, or text to the bits and text back out. In the case of QPSK 31, it's got an extreme amount of error detection and error correction. So that's why you can be such a narrow bandwidth. And even with a lot of noise, it'll say, oh, I can tell the difference between that's noise. I missed that bit, but it's echoed 3 bits later. I can get it from there. And all this stuff is going on in the post-processing. And that's it. But pretty much everything over the air is either frequency, phase, or amplitude modulation. That's all you can do. And it all looks something like this. All the smarts go into it before and after. Okay, just 2 more slides. So this is a concluding slide about the 8920. And it has so much more than those instruments. It has, I'm going to just read this, save recall registers to hold complete instrument states. And the amount of storage depends on what you store and its difference from preset. So it actually uses dynamic storage. It only stores settings that you change from their preset state. So you get at least 50 to 100. I've got about 100 in my test set. But this saves the complete state of the instrument. And if you ever get, so you made a lot of changes, you save it, and at least you can get back there with a single recall and continue changing it or do other things. It has a built-in instrument basic controller, so you can plug a keyboard into the rear panel, and it lets users write their own radio test software, including this box will actually control other devices using HPIB. That's a interface standard, or IEEE 488. Actually, HP released it as a public standard, and it's IEEE 488. So other companies have their instruments on it too. But this is a controller. So you can control a printer, a disk drive, a second signal generator, whatever you want. Do complete automated radio tests and print out results without ever touching the radio once it's hooked up. We sold two industry standard iBasic test software suites to test a particular family of radios. So a lot of times they'd buy a 8920A plus this software package, and it's everything they need to do their tests on the manufacturing floor. It includes self-tests and diagnostics. Because it has so many sources and receivers, it can diagnose its own problems. So it connects the signal generator to the analyzer, or the audio source to the audio analyzer, figures out what's wrong. This iBasic language even allows 3D graphics stuff. And back in the 1980s, I started getting interested in three-dimensional graphics, and I wrote this program on the test set to do hidden line removal on a surface. So that was just a program that I wrote back then and got paid for it, even though we didn't use it. People wanted to know, will the graphics commands really work? And I said, okay, I'll exercise them and try and do that. Okay, so a review. We've covered 3 hardware scenarios: over the air 0 cable, a 1 cable, and a 3 cable. We went at least mentioned RF frequency error. These are transmitter tests: transmitter power, spectrum analysis, FM deviation, audio frequency, audio distortion, various oscilloscope things, microphone sensitivity, PL tones, or the tones for repeaters. We measured their frequency and FM deviation. We measured DTMF tones. For the receiver, the all-important receiver sensitivity that used SYNAD, or that, just remember, 12 dB SYNAD is, I definitely hear a pretty strong noise behind you, but I can still hear you okay. That's kind of a 12 dB SYNAD, and audio AC level. So any questions or comments?
I guess
Okay.
it doesn't test adjacent channel rejection, that kind of thing. Did they ever do that?
Yes, and the reason I didn't do that is adjacent channel rejection. Well, there's 2 ways you can. The actual way you're supposed to do that is be listening to a signal at the same time you put a signal 1 channel away. And that takes a second signal generator. And remember, one of the things I mentioned here on the basic, this one, this is a common thing to do, is you get a second signal generator for adjacent channel power tests. Now you can do that approximately by having nothing in your existing channel. This is just more of a functional test. It's not the way the test is supposed to be done. And put a very strong signal in the next channel over and see if you hear it. And that's not the spec, the official EIA way to do the spec, but it still gives you a pretty good indication. And you know, in other words, you can be listening to noise, you know, have your monitor on and be listening to noise, and just run the signal up 1 channel away until you do hear it, and then see what level that was. Is it, you know, how many tens of dBs higher than a normal signal was it? And that's a rough indication of adjacent channel selection. You know, you hope that it'll just keep going up and up and up and up, and you'll never hear it, but that isn't the case. That's it.
What about desensitizing?
Yep, and so all of these tests can be done, and you're getting into, so I wanted to keep this pretty generic and the simple ones, but desensitizing is when you're listening to like one of these 0.1 microvolt or 1 microvolt signals. So you're using your radio in a normal situation, and nearby you have well, it's pretty much the same as adjacent channel, but this is like nearby. So it could be 10 megahertz away, but you have a 100-watt transmitter transmitting on an antenna. And this now can actually desensitize the entire receiver. It won't receive anything because there is so much power coming in the antenna. It just overdrives the front end amplifiers, and they don't function right anymore. And do this too much and you can actually damage the radio, but generally that's not the case. And it just means that your radio won't even receive anymore in the presence of 100 watts 10 feet away, you know, or something like that. But you can measure that. And there's actually specified ways to measure it where you put off at a certain frequency a controlled very high signal, like 80 or 90 dB above what you plan to be doing. Any other questions? Yeah, there's a bunch more measurements in the EIA test suite, and radios have to go through them too, but I'm just taking you through the most basic ones. These are ones that are pretty much always on the spec sheet, that kind of thing.
Well, I just wanted to say that I have an oscilloscope, an RF generator, an AF generator, a multimeter, a frequency counter, an SDR dongle that will show me, you know, any besides the SDR radio, but an SDR dongle would also show us those harmonics. And I have a DTMF reader, a Surecom, which reads the DTMF frequency, SWR power meter, and all of that equipment doesn't do what this thing does. So
Yeah, it really is a manufacturer. It's primarily a manufacturing or business service market. Hams did not buy this thing. You know, I got one other side story, but once we took this to the Dayton Hamvention, 1992 or 93, I think, we went to the Dayton Hamvention because so many hams are also in business for radio. And we did get a lot of good contacts at our trade show booth. But one of the things I did for the trade show was tone sequential signaling can actually simulate Morse code. So for the duration of the show, we had the volume just so you'd hear it if you walk by the booth, but the test set was transmitting B-U-Y-M-E, pause, B-U-Y-M-E. And people would go by the booth and hear this Morse code and they'd get there, you know, because even though there's a lot of hams, there's not a lot of Morse code. And they'd say, where's that coming from? And they'd look directly at the test set, great marketing, and go, oh, I see. And what is this? You know, but anyway, so we had the test set sending through its speaker by me. But anyway, no hams bought it, but people that had it for business, you know, they'd give us their business cards and say, here, send me some information, stuff like that.
Well, Rick, I'm not sure you mentioned it in your talk, but maybe everybody here just knows because you and Jack worked there, but they're manufactured right here in Liberty Lake from the beginning, right?
Yep. Yeah, this was, the boards were actually assembled off site with surface mount and stuff, but the boards were all designed part by part, Liberty Lake. And that was by that, I did mention at the beginning, 2 mechanical engineers, 10 electrical engineers, 8 firmware engineers. For the last about 3 years of the project, that's how it was staffed. And everybody was busy and doing iterations on their boards. And then what this box had to go through for testing before we shipped this box too, it goes on shaker tables for G-force measurements and temperature and humidity chambers where you put it where it's practically raining in the test chamber and heat it up to, you know, you check the specs on this thing. It's supposed to be able to be carried up on a mountaintop in 110-degree weather and still measure in spec and that kind of thing. And also the testing this goes through. I didn't mention the manufacturing engineers. That's true. So they're the ones that do the testing and the shake and shock, temperature, humidity, and tell us, nope, it failed, redesign this board, redesign that board, all that stuff. So it's a long process to get something like this out.
Yeah, and are there other guys around from that project, from that plant, who are still active in ham radio?
Yes, in fact, I talked to several of them Sundays at 3 o'clock on the North Idaho repeater system, but Jim Summers, KD7F, Brian Miller, N7IP, he's always there. Oh gosh, we actually had a ham club at Liberty Lake. Remember that at its peak, it had 2,000 employees out there and we had 50 hams. So this is 50 hams out of 2,000. That's way above the national average. So this place was just a magnet for ham radio operators. And Yes, every ham operator, in fact, had input on, oh, you should make it do this. Oh, you should make it do that. And if it was only a firmware change, pretty much I did them all. That was, that was so you might notice back on the block diagram, the audio analyzer has the 4 main inputs, AM, FM, single sideband, and audio in. And then there's one line that says 6 other inputs. And that's 6 inputs from various areas of the block diagram. So you can do cross-coupled signals and demonstrations and self-diagnostics and all that stuff. And a lot of that stuff came from suggestions from ham operators that said, hey, if you just connected it here, we could do audio analysis on the IF signal or on this or on that, you know, and it's got a lot of extras that you can do.
Okay, Randy's showing off now. I have and I have equipment lust or envy.
Okay, well, so maybe you guys knew Lee, W7MW, a longtime member of VHF Club, and worked for the Hewlett-Packard plant there in Liberty Lake. And I bought this one from him, and it is one of my prized possessions, that's for sure. This one was factory refurbished. It still has the factory calibration sticker on the back. All the knobs are shiny and clean still. I feel like I was lucky to get this one.
Yep. Let me
I
say
was gonna
something.
say-
Lee passed away either 2 or 3 years ago or whatever, but it was actually I used to have lunch with him and other ham radio friends once a week. And it was actually one of our lunch friends that that talked to him even more regularly, that didn't hear from him, went to his house and actually found him. And